Hello, everyone, and welcome to our first ever online RSS West Midlands local group event. Really excited to be hosting this. Just as a matter of order, we've been around for about about 75 years. We're coming up this year, and pretty much every event for the last 75 years we've kept an attendance record. So we'd be really grateful if you could, in the chat, just put up your name, say hello, let us know you're there. If it's possible to also say whether you're a fellow or not, then that would be great. We have records of that. First thing to say is thanks to David Selby, who is a member of our committee and is putting this together all technologically. So a big thanks to him. Second, I wanted to mention a point of order. So during the talk, what we'd like to do is if you have questions, put them up on the YouTube chat, and we'll collate those, and then we'll put them to Marius at the end. There'll be time for that. And the third thing is just to say, if in our virtual pub you want to let us know what it is you're drinking, then please do that too. It would be great to hear from a few more of you that way. With all of that said, let's crack on. So speaking to us tonight is Marius Ötting from the University of Bielefeld. This session came about because I saw his paper in Series A last year, and it's a subject that I'm interested in, both the hot hand behavior and the darts. And I thought it would be a great excuse for holding a session in the pub. Unfortunately, with circumstances being as they are, an actual pub was not possible and didn't appear to be possible maybe for some time to come. So we decided it would be a great opportunity to give some people a chance to sign into an interesting talk of an evening. And so we decided to do it in the virtual pub. So we've invited Marius to come along. As I said, he's a PhD student at the University of Bielefeld. He's specializing studying in sports statistics, in particular looking at betting fraud detection and performance evaluation. But what he's going to talk to us about tonight is the hot hand behavior in darts. So with that, over to you, Marius.
Yeah. Okay. Hello, everybody. I hope you can all hear me. So I'm going to share my screen now to share the slides. Okay. Yeah. So hello, everybody. And yeah, thanks first of all to Ian for the introduction, and thanks also for organizing all this, for setting up this event in these tough times. I'm really happy here to be today here in this online seminar, Stats in the Pub, so in the virtual pub, to give a talk here, and also thanks to David for setting up all the technical stuff in the background here with the live stream and so on. Okay, yeah, so my talk today is entitled, Does the Hot Hand Exist? An Analysis of Professional Darts Using State-Space Models. So when we talk about the hot hand, the first question, of course, is what actually is the hot hand? So in sports, the idea of the hot hand refers to the concept that a player may enter a state where he experiences exceptional success. So for example, in basketball, if a player hits several shots in a row, then the commentators of the match often say that this player has a hot hand, or that he is on fire or in the zone. And the hot hand has even made it into some video games. So here, this is a screenshot on this slide of the video game NBA Jam, which is rather old video game. But here in this game, if a player hits several shots in a row, then his hands warm up. And if the player hits like very, very many shots in a row, then his hands are even on fire, so representing a hot hand effect here in this video game. But however, whenever we talk about the hot hand, so lots of people in sports like commentators or fans and also players, they really like to believe in the existence of the hot hand. But the question is whether the hot hand really exists, so whether there really indeed is serial correlation in performance or not. So to introduce you a bit more to this topic, I will first show some of you, I'll show to you some of our data. So these are the throwing sequences of Peter Wright. So Peter Wright is the current darts world champion, and these are the first 8 throwing sequences here in our data. So the zeros here, they mean miss, and the ones, they mean hit. What exactly we define here by hit and miss, I will come to that in a minute. But for now, if you look at such binary sequences and you're investigating a potential hot hand effect, the question always is there some serial correlation here in these sequences or not? So by looking at these sequences, some of them maybe look like that there should be some serial correlation, while for others it's not that obvious to decide that just by looking at these numbers. So if there's some serial correlation here in these throwing sequences, this would support the hot hand hypothesis. On the other hand, if there's no serial correlation, this would mean that the hot hand is just a cognitive illusion. And yeah, it's hard to decide just by looking at these numbers. So by comparison, we can have a look at some realizations of independent Bernoulli trials here, which I generated in R. So we have 5 sequences here, each sequence of length 10. And for example, in the third sequence, there are 5 successes in a row. So someone maybe who really likes to believe in the hot hand and who doesn't know about the data generating process would perhaps interpret these 5 successes in a row as evidence for the hot hand effect, for the existence of the hot hand. And indeed, by using such simulated data with the underlying IID process, there are several studies who provide evidence that humans indeed often overinterpret such streaks of success and failure in random data. So in such random data, these studies show that humans often look for patterns in such random data which look somehow non-random and interpret these patterns then as evidence for the underlying data generating process being not independent. So here in this case, this would mean that, or this would explain why some people really like to believe in the hot hand. So the belief in the hot hand could be driven by simply over-interpreting such streaks of success and failure in data where the true data generating process is IID. But however, in sports, of course, it's not that easy. We don't know the true data generating process. So there's been lots of research going on in sports on the hot hand. So research started in 1985 by a paper by Gilovic and his co-authors who analyzed free throws in basketball. So they analyzed conditional success probabilities. So they estimated the probability of a player making a shot given that he also made the last shot versus the conditional probability of a player making a shot given that the player failed at the last attempt. And by using that approach, they found no evidence for the hot hand, and they labeled the hot hand a cognitive illusion, and they also coined the term hot hand fallacy. However, since then, almost 30 years ago, more than 30 years ago now, the hot hand has been investigated in many studies. So some of them, so really just a very brief overview here. Some studies focus, for example, on baseball or volleyball, bowling, and of course basketball again. So this paper here on the slide by Miller and Sanchuro from 2018. This is quite interesting because they highlight a bias in the test statistic, which was used in the original paper by Gilovic, and then they provide a bias correction in this test statistic. And then they used the original data, which was also used by Gilovic in the original paper from 1985. And using the original data, in addition with together with the bias corrected test statistics, they even provide evidence for the existence of the hot hand. So things have changed a bit there. And also some other more recent studies, for example, the one listed here at the top of the baseball study by Green and Swiebel, they also provide evidence for the existence of the hot hand. But it doesn't matter which of these sports you look up in the literature. There are many studies, and most of them refer to two types of approaches. So the first approach to investigate a potential hot hand effect is to analyze the outcomes. So these binary sequences, for example, which we've seen on the previous slide, and by using such binary sequences, one can, for example, estimate, like Gilovich did it in his paper, estimate conditional success probabilities or compute serial correlations. Another approach is to use a latent variable instead. So this latent variable serves for the underlying not observed form of a player. And this latent variable could, for example, take the values hot and cold. So if the player is hot, then his success probability is above average. And if the player is cold, then the success probability is below average. And here in our study, we also refer to the second approach, so to the latent variable approach, because we think that this approach is more aligned with expressions such as being in the zone. But I will come back to that again in a minute. So as the hot hand, generally defined, means serial correlation in human performance, and there are lots of studies in sports, but the hot hand also refers to a more general setting. So the hot hand can also be investigated in other settings, such as, for example, careers, or a hot hand among hedge fund managers, or a potential hot hand effect in gambling activities. So gambling activities is a bit of a special case here, because for casino games, we of course know the true data generating process. However, by such studies, the authors again found evidence that humans really like to believe in the hot hand, or on average believe in the hot hand, even in settings like gambling activities, so casino games, where the true data generating process is IID. Okay, so this brings us to our data here. So we investigate the setting of professional darts. Just to sorry for the short interruption here. So I will come back to the data. So we are investigating here the setting of professional darts. So why are we looking at darts here? So the main reason for that was because most of these previous studies, so if we go back to the sports studies, so there are lots of studies investigating the hot hand in sports where interactions between opponents are present. So for example, in baseball, there are interactions between the pitcher and the batter. So if you analyze the hot hand of a batter in baseball, the performance of the pitcher is of course also important for that, but it's a bit difficult to account for the performance of the pitcher. And in addition, we in settings like baseball, you have lots of potential confounding factors, for example, weather conditions. So to clearly identify the hot hand effect, you have to somehow account for the interaction between opponents, and you have to account for these potential confounding factors. And that's why we've chosen darts here, because in darts, there are no interactions between players. Darts is a very, very standardized setting. So that's a very, very clean setting, which is great for analyzing the hot hand. And there's lots of data freely available online. Yeah, so that was the main reason why we have chosen the dart setting. Little spoiler here already, although we thought that the darts is a very, very clean setting where which is quite perfect for analyzing the hot hand. It turned out at the end I will come to that later, but it turned out that darts is maybe not that 100% ideal setting, because also the darts data had some caveats, but I will come back to that later. So first, although we're here in these in the stats in the pub seminar, and I think most of you are familiar with the game of darts, I will shortly introduce the rules of darts very briefly. So this is a standard dartboard, which is divided up into 20 slices, and each slice is further segmented, separated into 3 segments. So the single, the double, and the triple segment. And for example, for the 20, so if you hit the black segment in the 20, this gives you 20 points. The double segment at the top gives you 40 points, and the triple segment, of course, gives you 60 points. The bullseye in the middle gives you 50 points, and the single bull in the middle 25 points. And at a darts match, so darts is always played one-on-one, and at a darts match, players start with 501 points each, and the first player who reaches exactly 0 points then wins the leg. And the first player who wins a number of legs, so this number is pre-specified, then wins the match. So when the darts match starts, players start with 501 points, and as they have to reach exactly 0 points, they at the beginning want to very quickly reduce their score to 0. So at the beginning they aim at high numbers, and at every turn they have 3 darts to throw, which are then thrown in very quick succession. So at the beginning, they aim at high numbers. So for example, at the triple 20 or the triple 19, most players go for these numbers. I will also have some descriptors on the next slides. Our data also indicated that sometimes some of these lower triples are aimed at. So for example, triple 11 to triple 17. And we include these triples also in our set H, and every throw which then lands in this set H, so which is defined from triple 11 to triple 20, and the bullseye is then defined as success. And as at the end of the match, players do not aim at H anymore, because they have to reach exactly 0 points. So that's why we cut the time series then after the player has reached 180 points. Okay, so this data here was taken from dartsdata.com and covers all tournaments between April 2017 and January 2018. This gives us several binary time series, which we denote by Y here. And P is the index here for the player, and L is the index for the leg. So one time series here consists of 1 leg played by 1 player, but of course in our data set we have multiple legs played by several players, and we restrict our analysis to players who have played at least 50 legs in the period. We have our data set here, and this then gives us 170,000 or about 170,000 dart throws taken by 73 players. Okay, so here are some descriptives. So we see the triple 19 and triple 20. Most players go for these fields, but we also see that the other triples are also hit from time to time, with the triple 11 to triple 16 being very rarely aimed at. We included these numbers still here in our set H as success, because our argument is here that if players if players hit these fields, so for example the triple 12, they wanted to hit this field, they aimed at it, and that's why we included these throws also in our set H and defined them here as success. Okay, when we further investigated the data, we saw that the proportion of hitting H increases during a player's turn. So for example, in the first throw of a player's turn, the empirical proportion for hitting H is 35%, whereas for the throw number 3, the proportion of hitting H is 42%. So the hitting H becomes more likely within a player's turn, and this is something we have to account for later on in the model formulation. Yeah, this brings us to the model formulation of the hot hand. So how to model a hot hand effect. And what we have, what I've mentioned in the beginning, in the introduction, is that there are mainly two types of approaches which have been used in the literature. So either to focus on the outcomes, so to, for example, calculate conditional success probabilities or serial correlation directly of the outcomes, or to use the latent variable instead. And here we also use a latent variable which serves for the underlying form of a player, because we think that this approach is more aligned with expressions such as being in the zone. And indeed, a similar approach has been used by Green and Zwiebel in 2017, but they distinguish between three different states. So they distinguish between cold states, normal states, and hot states. But here we thought that players do not, that the underlying form of a player is not discrete, so that there are lots of things between cold and normal, and between normal and hot, and maybe there's something like a super hot or super cold state. So what we're thinking here is that the form of a player is rather continuous valued and not discrete. So discrete is of course very easy for interpretation, but we think that a continuous valued state process here is better for describing the underlying form of a player, because it allows to model also gradual changes within a player's form. Okay, so this brings us then to state space models. So in state space models, we have two model components. So the first component is our observed binary sequence, so our data which we've seen on the first slides. And this is denoted again by Y here, and by ST we denote the unobserved state process, which serves for the underlying form of a player. And as our variable Y is binary, we of course assume the Bernoulli distribution, and the success probability denoted by pi here is then linked through the log@link function to our linear predictor, and our predictor depends on the current level of the state process. And the state process then depends on the value of the state process of the previous time point plus an error term. So this figure here makes this maybe a bit more clear. So here at the top we have our YT, so our observed binary throwing sequence. And at the bottom we have our latent state process, which serves for the form of the player. And for the state process, we assume the Markov property such that the level of the state process at a given time point depends only on the level of the state process at the previous time point. Okay, so this is the dependent structure here for our model. And next question is then how to formulate the likelihood for such a model. So the likelihood involves integration over all the possible realizations of our state process ST, which is intractable. So we apply numerical integration here, and this numerical integration effectively leads to discretizing the state space. So we have at first to choose an essential range for the state process, which is given here from B0 to Bm, and this essential range is then split up into m intervals of equal length. And given that m is fairly large, so for example m equal to 100 is already sufficient. So with m being very large, the continuous valued state process can then be discretized and hence approximated. And how does that look like then? So we have here at first our multiple integral, which we can then reformulate given by our dependence assumptions of our model formulation. And then each integral is approximated by the corresponding sum. And the bi star here denotes the midpoint of interval bi. And in this multiple sum, we simply sum over all possible combinations of the state sequence. And this then gives us the likelihood. However, this is a bit of a problem here, because in this multiple sum, we have m to the power t terms in this sum. And given that m is already quite large, so m is equal to 100 or even larger, and t can also be quite large. So the computational cost associated here with the likelihood evaluation is fairly high. So this is a problem here. However, the discretizing the state space here in this model formulation effectively transforms the state space model into a hidden Markov model, such that we can apply all the efficient machinery from the hidden Markov literature, and especially in this case here, the forward algorithm. And the forward algorithm then allows to reformulate the likelihood such that the computational cost is only linear in t. So how does that look like? That's given here on the slide. So we have to define first some quantities here. So we have to define a quantity for the initial distribution. So the initial distribution is given by the vector delta. Delta is a vector of length m, and each element in this vector gives the probability that the state process at time point 1 starts in that state. For switching between the states, we have a transition probability matrix, and this is denoted by gamma here with entries gamma ij, and these include the probabilities for switching from state I at time point t minus 1 to state j at time point t. And for the observations, we have our diagonal matrix, which we denote by P here. So this is an M times M diagonal matrix. And the ith diagonal element is then equal to the probability of Y given that we are in state I. And by defining these quantities, we can then calculate the likelihood by the matrix product as shown here on the slide. And this by reformulating the likelihood in that way, the computational cost is increased substantially here. However, the likelihood as written down here on this slide effectively only applies to one leg played by one player. But of course, in our data set, as I introduced at the beginning, we have data from multiple players, and for each player we have multiple legs. So for the data set, for the likelihood, for the complete data set, we then assume that the individual legs are independent of each other, such that for the complete likelihood, we then multiply over all legs played by all players. And this likelihood is then numerically maximized in R, and for that we use the function NLM in R. Okay, so this brings us to the results. So for the results, we first have a benchmark model. And this benchmark model, which we denote by model 1 here, is a simple logistic regression model, so no hot hand effect involved here. We have an intercept for each player. And in addition to this player-specific intercept, we included 2 dummy variables here, which indicate the second or the third throw within a player's turn. And this is included because we have seen in the beginning in the descriptives that the proportions of hitting age are increased during a player's turn. So that's why we include these dummy variables here. So this is our benchmark model. And the first hot hand model, so model 2, is then simply the benchmark model plus the state process. And for the state process, we assume an autoregressive process of order 1. And the main parameter of interest here is phi. So if phi is equal to 0, this would mean that there's no persistence in this latent form of a player. So this would mean that we have no hot hand effect. Whereas if the phi is greater than 0, this would support the hot hand hypothesis. And for the initial distribution of the state process, so for the distribution of S1, we consider 2 slightly different distributions. So we assume normal distribution here with the mean dependent on whether the player won the previous leg or lost the previous leg. So we simply assume 2 different means there. Okay, so the corresponding likelihood is then numerically maximized, and we approximate the continuous valued state process by 150 states. And maximizing the likelihood then gives us these results. So the main parameter of interest here is the parameter phi. So this is estimated at about 0.5. So the 95% confidence interval does not include the 0. So here, with the persistence parameter estimated of 0.5, we have found quite strong evidence of serial correlation in throwing performance. Beta 1 and beta 2 are positive, as already expected from the descriptive statistics. And if we take a look at the means for the initial distribution, we see that both are estimated negative. So at the beginning of a leg, players start with a form which is slightly below average. And interestingly here, if the player lost the previous leg, then the 0 is not contained in the confidence interval. Whereas if the player won the previous leg, then in the confidence interval, the 0 is included here. So at the end, we compare our model to our benchmark model, and the difference in the AIC is 550 points, such that also this model comparison via the AIC provides evidence for serial correlation here in throwing performance. So while this model formulation is nice and clear, and yeah, we can fit it to the darts data, and that works fine. The results are also quite nice. However, this model does not fully capture the structure of a darts match, because at a darts match, players throw 3 darts in quick succession, then they have a short break, and then they throw the next 3 darts. So if we look at the dependent structure again, here in the so this is shown here in the figure for the second turn of a player, where he throws dart number 4, 5, and 6, and between dart 4 and 5 and between dart 5 and 6, we assume that the transition there, so the transition within the player's turn, is somewhat different than the transition from dart 6 to dart 7, because between dart 6 and dart 7, the player has a short break, and in this break, the opponent takes his turn. So explicitly accounting for these breaks in a player's turn slightly changes our model formulation, which brings us then to model 3. So the state process is now not an AR1 process, but a periodic AR1 process, such that we have 2 different AR1 processes, so to speak. So one process for the transitions across players' turns, which is given in blue here, and one process here for the transitions within players' turns, which is denoted here in orange. So the corresponding likelihood is then again numerically maximized, and these are the results here. So for the persistence parameter in our state process, which indicates the serial correlation in throwing performance within the player's turn. So this phi W is estimated with 0.7, so fairly large, and the corresponding confidence interval does not include the 0. However, the parameter phi A, so for transitions across players' turns, is estimated at 0.06, which is fairly low, and the corresponding confidence interval does include 0 here. The rest of the parameter estimates are more or less similar to model 2, but what we found here is fairly strong evidence for serial correlation within a player's turn, but the underlying form can then not be retained by the players across turns, because the phi A is very small and the confidence interval even does include 0 here. However, when we compare this model to model 2 by the AIC, we see that this model here is preferred by the AIC over model 2. Okay, so up to now we have found serial correlation in throwing performance. However, this effectively applies only to the darts thrown within the player's turn, and the underlying form of a player cannot be retained across turns. So up next, we will do some model checking here in 2 steps. So in the first step, we have a look at the sequences within the player's turn. So going from 0, 0, 0, so miss, 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 all sequences until 1, 1, 1, so hit, hit, hit. And for each of these sequences, we look up the empirical proportion in the data, and then we simulate data from model 1, model 2, and model 3. And using this simulated data, we again calculate the proportion of these different sequences under the simulated data, under the fitted models. And what we see here is that model 1 clearly over and sometimes underestimates the empirical proportions found in our data, whereas the hot hand models, model 2 and model 3, capture these empirical proportions way better. So this again is a bit of evidence here for a serial correlation in throwing performance. So this was a model check for the throwing sequences within the player's turn. Up next, we will have a model check for the throwing sequences across players' turns. So here in the first column, we have the pairs. So what does that mean, these pairs here? So pair 0, 0, for example, means that the player did not hit any triple in the first turn, and in the second turn, he also didn't hit any triple. Whereas, for example, pair 2, 1 means that the player hit 2 triples in his first turn and 1 triple in the second turn. And for each of these pairs, we all again look up the empirical proportions, which are given here in the second column, and then we again simulate data out of these three models. And using the simulated data, we again compute the proportions of the simulated data for these 16 different pairs. And again, what we see here is that model 1, so the benchmark model, often over or underestimates the empirical proportions, whereas model 2 and model 3 capture these empirical proportions way better. So our hot hand models here capture the structure of the data way better than the benchmark model 1. So this again is a bit of evidence for throwing for serial correlation here in throwing sequences. So when we were at that point with the paper, we thought, oh, okay, that's quite nice. I mean, we have a nice setting with darts, a very large data set, a nice model formulation, and the results also look fine. But then, so I mean, up to now, our results they suggest that there's a hot hand effect, which more or less only applies to the darts thrown within the player's turn, because the underlying form cannot be retained across turns according to our model. So this was our main result. And then we submitted the paper, and then the associate editor had some very insightful comments, which were very helpful. So they were somewhat darts related, because yeah, up to now, our results look like they provide strong evidence for a short-lived hot hand effect. But the associate editor then told us about marker darts. So a marker dart is typically the first dart thrown by a player, and if this first dart hits the triple segment or is slightly above the triple segment, then the player can use this first dart as a marker, in a sense that he can use this dart as a wall, so to speak, where darts 2 and darts 3 of his turn, he then aims at this first dart, so at this marker dart, and the dart, the corresponding darts are then deflected from the marker dart right into the target. So we already have seen that a bit, because in the descriptive statistics, we have already seen that the proportion of hitting age is increased during a player's turn. So the empirical proportions for hitting age were way higher with dart 2 and dart 3. So yeah, somehow our data already indicated that a bit, but we weren't aware of these marker darts. However, our data unfortunately does not indicate whether a dart thrown is a marker dart or not. So we simply cannot rule out that these results may be in fact driven by these marker darts, because yeah, I mean, we have found with our parameter phi w, we have found very strong evidence for serial correlation within the player's turn. But now with these results, so with these marker darts now, we simply don't know whether this large value of the serial correlation within players' turns is indeed driven by a hot hand effect, or simply the reason because of these marker darts. Yeah, that's something we don't know, and this gives us a bit of inconclusive results here at the end, unfortunately. Yeah, okay, so what can be done for future research? So first part is to reduce the computational cost. So the code was mostly written purely in R. So parallelizing the code and writing some of the code in C++ would speed up the computation time substantially here, I guess. And this is something we're currently working on. The next point, so the second point here, is to extend the model framework to also allow our model to fit irregular time series. So with our darts data, we already had some irregular time series here. However, this in our setting, we could tackle that quite easy just by distinguishing between these two different parameters, phi across and phi within. However, in other settings, of course, we have highly irregular time series where there's sometimes only some seconds between two observations. Sometimes there are several minutes and sometimes several hours maybe. So extending our state space model framework to such data would then lead to continuous time state space models. So we have to formulate our model in continuous time, and this would change the state process, because the state process then is no longer an AR1 process, but the AR1 process is replaced by its continuous analog, which is the Ornstein-Uhlenbeck process, so a stochastic differential equation. And right now we're implementing this model to also allow for irregular time series for state space models here. Yeah, and another point for future research, something we have not looked into yet, but which would be of interest, of course, is to investigate the heterogeneity between the players. Because in our setting here, we assumed that the hot hand effect is the same across all players. So we had a single phi or phi across or phi within, but these parameters did not vary across players. But it may very well be the case that the hot hand ability, so to speak, that this is different between the players, so that there's heterogeneity between the players regarding a potential hot hand effect. We could incorporate that by using random effects for all the parameters of the state process. And this could then, for example, be tackled using a Bayesian approach. And this is, however, something we have not investigated yet. Okay, yeah. Here at the end, I will just want to highlight that all the things I've told you today are more or less based on the paper here, the Hothead in Professional Darts, which was published this year in JRSSA. And this is joint work with my supervisors, Roland Langelock and Christian Deutscher, and also with VNA Leos Barajas from the North Carolina State University in the USA. And if you're interested in the data or in the code for model fitting, this is already online. So there's a link in the paper where you can find the R code and the data. Okay, so that was from my side. Thanks for listening. And if you have any questions or comments, then feel free to ask in the YouTube channel.
So first, I'd just like to say thank you to Marius. I'm not sure what the convention is to say thank you on a chat, but feel free to be creative and say thank you in your own way on the chat. We do have a question. I have one of my own. So Marius, first question from Tim Davis. In reality, the set H only has one member at the start of the game, surely, treble 20. Could you talk around that a little bit? I guess maybe it's connected a little bit with the marker question, but maybe you could discuss that a little bit more.
Sorry, can you repeat the question? So it was around the triple 20?
So Tim's question was, in reality, surely the set H only has one member at the start of a game, treble 20.
Okay. So yeah, now I understand. Yeah, I will comment on that. I will look up these proportions here. Yeah, of course, most of the throws at the beginning, so most of the players go for the triple 20. This is also indicated here by this table by the corresponding empirical proportions. But however, our data indicated that sometimes players also aim at, for example, triple 18, triple 17, or even lower triples. And yeah, the main reason why we included these triples in our set H simply was because we thought that if these triples are hit at the beginning, the players really wanted to hit these triples, so that they aimed at it, and it was not random dart thrown, which was then hit in these triples. And another comment on that, which is maybe linked to this marker dart thing. So the opposite of a marker dart would be a blocker dart, which is so the definition of the blocker dart would be that this does not open up the area for the triple segment, but that this, so to speak, closes the area of the triple segments, such that if a blocker dart is thrown in the triple 20, the player cannot throw any more darts to the triple 20. So he throws then his darts to, for example, the triple 19 or triple 18 or whatever. So these darts in the triple, especially those in the triple 19, these are maybe driven by these blocker darts from the triple 20. I hope this answers the question.
I think so. I'll let Tim come back on the chat if he has a follow-up. I had a question around some of the other things I've seen around darts and statistical analyses of them. And I wondered if you could speak to them. So I know there was another paper a few years ago that looked at the left-handed, right-handed bias in darts. I wondered, I know it's not connected to your work exactly, but whether you could speak to that and what that came up with and the sort of approaches that have been shown there.
Yeah, thanks for that comment. Yeah, so there's a paper on the left-hand bias in darts. I think the left-hand bias in general is something which has been investigated in different sports, or also in tennis, for example, whether left-handers have an advantage or maybe disadvantage there. So that's the main idea, and this has also been investigated in darts. And in their study, they have some experimental setting, I think, where they invited some amateurs to throw at the dartboard, and they compared the scores of the right and left-handers, I guess, and they found that the left-handers, that they score less points on average, and they then come up with a bias-corrected dartboard where the expected value in some sense is equal for right and for left-handers. Here in our setting, I think it would be interesting to maybe to see if there's any difference. So this applies a bit to the outlook at the end, where I talked about the heterogeneity between players. This could also be a thing to see whether there are some differences between left and right-hand players. So I'm not that sure, but I think there are some left-handed players on the Pro Tour of the PDC. So this would be of interest, of course. And another thing which is a bit related to that would also would be gender differences. So in our data set, unfortunately, we only had men and no women. But since the last PDC World Darts Championship, there's also at least some data for some women. So this would also be of interest to compare these to check whether there are any gender differences in darts. Maybe also regarding a hot-hand effect. Okay,
thank you. One final question from me. My understanding was that the Miller and San Giorgio paper that you referred to earlier actually questioned some of the mathematics in that first paper, the Gilovich paper. I gather that was quite a subtle point, but quite a nice point. Could you possibly talk about that? Are you familiar with it?
Oh, I read about this this bias, but I mean, I can skip to that slide. Yeah, so it's some sort of selection bias they find in the original study, but to be honest, right now I cannot give you a full instruction to this bias they find there. So I think the main idea is not in this in the bias they find is not that hard. I mean, there's lots of mathematical work going on there in their paper, but right now, to be honest, I don't remember the exact bias there.
That's fine. It was a bit cheeky me asking you about someone else's paper, but I wondered. I think first time I read it, I didn't understand it, so I thought I'd try and get someone to explain it to me. But that said, there don't seem to be any more questions on the chat. But really, I'd like to say thank you very much. Marius has been a great sport in adjusting his plans to make this happen. And so I'm very grateful to him for that. There seems to be a lot of appreciation on the chat, and certainly appreciation from us at RSS West Midlands. So with that, thank you very much, Marius. And hopefully this is the first of a number of these. So yeah, watch out for the notices in future, and we'll give you a bit more warning than 2 days next time.
Yeah, that's great. Yeah, but thanks again for setting this up. I really enjoyed that, and yeah, I was really happy to give a talk here in this stats in the pub seminar, and yeah, I'm already excited to see what kind of talks will be followed up in the next week organized by you.
I can't promise in the next week, but any suggestions, do let us know. All right, with that, thank you very much.
Yeah, thank you too. Bye.